Good evening, good evening. So let us look at the next few topics. যেটা আমরা এর আগে দিন করেছিলাম, the ones we talked about. How are you doing with that? Is it okay? Good. So we will start with the technology part. This time I have not covered everything because of the whole online story. And if I covered everything, then you will just have to struggle a lot. So the syllabus has been condensed. Uh, so here we go. So, do you see the screen? Okay, so this was what we did, yes. And so from that, we go to the silicon manufacture process. So that is the technology component. I think you have this PowerPoint already in the classroom, right? I just took it from the classroom. So did you notice this? Yes, it's there in the classroom itself. Okay, okay. So which is why I thought instead of looking at my notes, I'll take whatever is there in the classroom so that you're not confused. Okay, so here you go. Silicon manufacture. So starting point for silicon is sand. Okay, and sand, of course, is quartzite. It's silicon dioxide, so to speak. Okay, and if you look at the picture, can you see the picture here? So that is sand, and if you look at it, notice the grains of sand have roughly the same size. The size distribution in sand is quite small. Okay, so each grain of sand is a crystal. It's a crystal of quartzite. So I'll not go through the entire steps because you can read it yourself, and it's not a big deal. And if you look at it, see that you convert it with, and you get this equation. See the equation here. Can you see the equation? I don't know. Hold on. Is my voice fine or is worse? Hold on just a second. Let me go to a different. Hold on. Hello. Okay. So is it any better? Okay. So that's the possibility. Okay. So if you look at this, can you see the picture now? Okay. So the picture is that of sand, and the sand is quartzite, is silicon dioxide. So the starting point is you take the sand and then you heat it in a arc furnace at a blah 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 temperature. In presence of carbon, so carbon reacts with silicon dioxide and forms silicon and carbon monoxide, which is of course a gas. So that's the first stage of purification of silicon. Okay. Now the problem is obviously this is not a good quality of silicon. So that it's called the metallurgical grade, and all the details are there in the slides. So how do you purify this? The way to purify this, that you react this metallurgical grade with HCl. Okay. So if you react with HCl, and then you get these things. Can you see the names? Silane. Yes. So methane is what? CH4. Silane is HiH4. Okay. And then the chlorosilane is simply SiH3Cl. Dichlorosilane is SiH2Cl2, etc., etc. Okay, so you replace one hydrogen with the chlorine, you get the chlorosilanes. So if you react silicon with HCl, you get these, of which this trichlorosilane is a liquid. Okay, so how do you purify liquids? You purify by fractional distillation. So this is how trichlorosilane is purified. So you know what is fractional distillation, right? Okay, so that is carried out enough number of times until you get very high purity, and then you convert the thing back to silicon back again by reacting with hydrogen. So this now is very pure. So that is the electronic grade silicon. But of course, if you see this lump, can you see this lump? Now that is obviously not a single crystal. It's a polycrystalline material. So the next step is to convert this into a single crystal. And the way to do that is something called the Czochralski process. It's said right here. And what it is, it's very simple. You take the words are out here. Okay, so let's look at it here, maybe. So you place it inside a crucible and you heat it up to melt it. Okay, and then after it is molten, can you see the melt? Okay, so after it's molten, what you do is you touch the surface with a crystal of silicon. Okay, now if you touch the surface, that is where the heat is being extracted. So the liquid around that surface is the coldest. And now if you cool it down to below the melting point, that is where it starts freezing. So that little seed now gets larger and larger. And let's look at it here. So this is the way it is. You you take here. Can you see the seed is touching the surface? Third one. And then as you start pulling up the seed, the solid part gets pulled up with it because basically the silicon itself is converting into a solid. Okay. And so this entire bowl, that's it's called a bowl, is pulled out. The whole thing is called the crystal pooling process. And this, it looks like this. And then you slice these, and then when you slice these, you get wafers. So that is the starting point of semiconductor manufacturing. Silicon wafer. Can you see those wafers like discs? Okay. Now, how do you dope? There's a whole process. I would like you to go through it. I cannot do it in a class very quickly, but let me try to explain something called segregation. Now, the question is, if I ask you what is a solution, what would you say? Definition of a solution, like a class 8 definition of solution. It is, for example, sugar is added to water. Where does the sugar go? Good. Now the question is, if I were to freeze the water, okay, do you expect all the sugar, the same concentration that was in the water, to remain exactly the same in the ice? Or do you think there will be a change? There will be a change. So that is what is called segregation. So if the dopant concentration in the melt is Cl and dopant concentration in the solid is Cs, then K, the ratio, is called the segregation coefficient. Okay. If K is less than 1, the solid gets less impurities than the melt. And mostly for most materials, K is less than 1. Okay. So knowing that in mind, so think about what happens when you're pulling it out. When you're pulling it, you're solidifying liquid to solid, right? So if you're solidifying, then what will happen if K is less than 1? The silicon is that is solid now is purer than the liquid. What happens to the excess impurity that should have gone into the silicon but did not? I mean, should have got into the solid but did not. That's right. So what happens to the concentration of impurities in the liquid? Right. Now, if you keep pulling up, what happens now? The ratio remains the same because, but then what that means, the second half or the second portion of the solid that's been pulled up is richer in impurities than the first part. So that is the whole story that you cannot get a uniform concentration of impurities. You will get some sort of a concentration gradient. Okay, that's all given out here. So this is like, if you look at it depending on the K and fraction pulled, how the concentration changes. Okay, so if you have any problem with this graph, you let me know, but it's pretty self-evident. This is just engineering. Now, obviously, then there's a problem. Impurities from the ambient is there, impurities from the crucible. What kind of impurities is given out here? It's and impurities should not be there. Okay, because then devices will not work. So next part of silicon manufacturing is to how to get rid of impurities. So for that, uh, there is something called the float zone technique. So let's look at this picture very carefully. So this is like a silicon rod which is held from two clamps. And there's a chamber in which the inert gas is being flowed out. So essentially, this is like no impurities are coming in from the surface. Okay. Now, what do we do is you take an RF coil. Now, do you know what is induction? It is a way to heat up by okay. So you take an RF coil very and bring it very close to the surface. You basically melt silicon at a small portion, like it's given in this picture. So this is why it's called the float zone because the top of the rod is like floating onto this molten region. Now the question is why does it fall off like a candle? Because of surface tension. It's very viscous, so it just stays in place. Now think about this very carefully. Now the RF coil is now moved slightly up. If it's moved up, then the lower portion, which was liquid, now gets solidified, and the upper portion, which was solid, now gets liquefied. Yes. Now, what will happen to the impurity? As it gets solidified, the lower portion gets purer, and the impurity gets into the liquid. To absolutely that. So, if you take this and then you keep pulling it up and up and up and to the top of the rod, and you stop, and then take it down. Don't push it down. Take it down to the bottom again, and repeat the process. So, what are you going to do? You're making the bottom part of the rod purer and purer, and essentially sort of like pushing the impurities up and up and up. Okay, so that is another technique for purifying. So it's called the float zone technique, and that is the interesting story. It's really interesting, and this is what it looks like. I have a picture somewhere. So this is what it looks like while you are pushing it up. So that's about it. Okay, and then generation of wafers. You take this rod, which in the grind and you polish, you slice, and then you there's something called chemomechanical polishing, where you polish the surface to make it defect free because there is something called slicing. If you look at the slicing, obviously you're using some sort of a saw. If you try to, then the surface is obviously damaged. So that the damage has to be removed by something called CMP, chemomechanical polishing, in which you use a powder, which is like a slurry, like a paste, which polishes the surface, and also some chemicals which etches the surface. So together you remove both the mechanically and chemically the surface, and then it looks like the picture that is there so that's the starting point of all processes of fabrication. Okay, so that is that, and then you develop notches or something like this so that you know what is pay type, what is p type, whatever. So that is just the knowledge. The next part is defects in crystals. So even if you do all of these things, there are also whole lot of defects present in this material, and there are point defects, line defects, area defects, and volume defects. Some of these defects are intentional, and some of them are not. So if you look at this process called doping, where you add p-type impurities or n-type impurities to a semiconductor, then it's a defect introduction which is intentional. But then there are other defects which are not intentional. Okay, so let's look at some of these defects. So first point is a point defect. Now, if you look at the first picture, if I assume the open circles are silicon and then the black stuff is an impurity, can you see it's called substitutional? Because it has substituted some of one silicon atom. And then the second one is called interstitial defect because it's not replaced, it is sitting in the interstitials, in the gaps between atoms. Okay. And the third one is called a vacancy in which one is missing completely. So where did that atom go? That atom has gone to the surface. So it's no longer a defect because the surface, of course, if there's an atom that goes to the surface and sticks there, the surface structure is no longer smooth, but that's not a defect per se, right? So that is a vacancy. And then there is something called a Frenkel defect, in which the atom has not gone to the surface, it's simply gone to the next position. Now the question, why do we care? So you know about defects, the one we talked about, like doping. Yes. So we keep telling, we introduce phosphorus in silicon. Now, why the hell will phosphorus get into silicon? And why should silicon give up its position for phosphorus? Okay. So the only way doping can happen is if there were vacancies anyways. And then phosphorus can take its place. Now the question is, why should there be a vacancy? Why should there be defects? Now, if you remember, last class we talked about why are crystals formed. We said that there's a minimum energy position. Now, if you heat up a material, what will happen? Does it stay fixed or does it oscillate? Yes. If you oscillate high enough, there's a probability that it will jump out of its minimum energy position. So then you get a vacancy. Now the question is, what is this temperature? Now, if it was classical story, then you need to go to very high temperature to get a vacancy because you have to break over. But then if you remember quantum mechanical stories, that there is a probability of this happening lower temperatures, even though it's a very small probability, but it's a finite probability of this barrier tunneling happening even at lower energies. Now, if you have a very large number of atoms which are trying to break through, and then you have a very large number multiplied by a very small fraction, you still get a reasonable. Okay, so that crosses over, and then that's the whole story. Okay, so that is that, and then there is something called line defects. So let's look at these crystals, looking at the bottom part. Okay, so how many atoms are there in the bottom row? Four, right? And then the above that is four, the above that is four, but just above that, can you see there's five? So an extra plane has somehow squeezed inside there. Why it has done that, we will talk about at a later stage. But if it squeezes inside, can you see that? That one atom has gone in where it should be. Now, how many neighbors does it have? Can you see it is one missing neighbor? So two because a covalent bond has to be shared, right? So one electron is not being shared. So that is a defect. It's a bond that is called a dangling bond. It's like an electron which is not being shared by anybody. Okay, so that is a defect. And if you realize that the atom just behind it, which we cannot see, has also that same defect. And so along that line, all atoms will have the same defect, which is why this is called a line defect instead of a point defect, because all atoms along that line will have the same defect. And this is called an edge dislocation. As you can see, edge, along that edge, there is a defect and it's a dislocation because the atoms have been dislocated, have been moved from its position. The next picture is that of a screw dislocation. And if you look at it, the screw dislocation, it's like the top part has been cut and moved around. Like if you remember a screw, the thread of a screw. So this is like it is moving around in circles. So that is another kind of a dislocation. If you want to know more about it, I've got another picture which is not here. Next time when we talk, I can show it to you. So why it looks like why is it called a screw dislocation? And so these are linear dislocations. And then we have area dislocations. Okay, point, line, and then area. Can you see in the perfect crystal, the stacking sequence of atoms are like ABC, 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 ABC. But in the defect, see that there is one in which there is a missing stack. Instead of A, B, and then C, you get an A again. So that is a defect, and it happens due to various reasons. But the most important story is this is for the entire plane is defective. Okay, so this is a planar defect. You understand? We're looking at it from the side, so that the entire plane is in a wrong position. And then there are volume defects, which are called precipitates, and you can see them like instead of like this actually happens for impurities. For example, if I'm trying to dope, phosphorus into silicon, I say, 2 million silicon and one phosphorus. But then what happens if you got 10 phosphorus atoms bounded together and 10 million silicon atoms? But then in this 10, it's no longer like an even solution. So then that becomes like a precipitate. So that is a volume defect. Okay. So these are the various defects that are there in the semiconductors. Why we talk about defects, you will learn in later classes, because what ends up happening is we there are two parts of this story. One part is we cannot get rid of defects completely because they are thermodynamically generated. So we better live with it, and if you have to live with it, better learn about it and try to see, okay, if you have to live with it, how do we mitigate it? How do we make it better without actually getting rid of it? That's one point. The second part is we use a whole lot of defect related modification of semiconductor properties. Okay, so we create defects in order to modify the proper behavior. And if I will go back up again, I deliberately skipped that in the first. Now, if you look at it, can you see the problems in Czochralski process? Now, the last bullet, it says oxygen can have advantages. So, defects such as oxygen can give something called mechanical strength. Okay. And then there is something called a gate error. Now, what is a gate error? I'll just try to explain it very briefly. If you look at a semiconductor wafer, it's 300 microns thick. Now, the devices are there only the top 10 micrometers. The rest is for structural stability. Okay. Now, what happens is there are a whole lot of impurities which you cannot get rid of. One of them, for example, is sodium. The others are, sodium comes from salt, which comes from basically human beings, sweat, for example, in the air. Anyway, the point is, if you cannot get rid of impurities, there's one more thing called a gettering. What is a gettering? We add oxygen deliberately to the back of the wafer and then heat it up. So when you heat it up, all the impurities start moving through the crystal because of the process called diffusion. Now, if it goes to the back of the wafer, then these impurities, whatever they are, iron, whatever, they get bound to the oxygen because the oxides are strong compounds, so then they cannot move back again. It's like the oxygen has gotten that. That's why it's called indicator. It has got it. So that what I'm trying to say is there are many, many ways. This is a whole industry which has been developed for 30 years. Millions of people have worked on it, so to speak, or at least tens of thousands of people have worked on it. So what happened is we have a very advanced technology. So impurities, the use of impurities in semiconductor devices by itself is a huge science and technology. Okay, so we're just wading into. All I'm trying to say is defects have their advantages. Okay, so that was the crux of the story. Now that is one slide that I wanted to discuss, and then we have CVD and epitaxy. That is the second story that is there. Okay, can you see my screen now? So here, what I will do is, let me be frank about this because I am a very practical person. There is no way you can go through this entire CVT and epitaxy from now till Saturday. So I will not give you any questions on my part from this part for the mid-sem. Of course, it will be there in the final exam. Okay. So just for your sanity, because it's just insane to expect you to learn everything in a week. So I will go through this, but there will be no exact questions on this on your midsem. Just our gentleman's agreement. So this is a picture that I have about various materials. Okay, so the top portion is about LED structure, and in the class I went through it in details, but I'll ask you to look at it, and then you'll realize that it's got a whole layer of stacks. When we say PIN, it's not exactly PIN. There are quantum wells, this and that, just to show that even a standard device like an LED, which no means people would assume to be highly sophisticated, right? We expect LEDs to be rather simple. You get it for 200 rupees or something, but even that has like 30 different layers of semiconductors of various thicknesses and compositions. So the whole concept is that electronic devices are extremely complex and extremely sophisticated. It requires control of or depositing or fabricating thin layers with exact tolerances of composition and doping and thickness, to the point that it is probably the most exact requirement of any technology in the whole world. There is nothing more sophisticated than a fab lab. Okay. So how is it done that you have to control composition and thickness and doping of so many different compounds? That very briefly is there in this slides. So this is for the LED, and then there is something for the MOS. So the top portion is the LED. Yes. No. Welcome to the real world. The white LED that you see, yeah, that is the point. Yes. This is the simple white LED. Yeah. I am sorry to break it to you, but yeah. And Santa Claus is not there as well. Sorry about that. So, yes, unfortunately. And each of them have their own very, very specific requirements. And if you could zoom in, when you actually look at it, zoom into, you'll see there are numbers like 34 and 29. So percentage wise, you have to be like that accurate. Uh, and the bottom portion is that of a CMOS, basic CMOS. So here also you have silicon or polysilicon, silicon dioxide, metals, C5 semiconductors, all of them are required. So the way it is done is something called chemical vapor deposition, and then this process, it goes through this entire vapor deposition process. It's like you have a surface, and then how the vapor deposition takes place. What are the six steps? You go through it. It's basic, you know, English. So I would not attempt to go through it very quickly. Now here is silicon deposition. Now this I would like to go through it a little bit focused. Now there are several sources for CVD of silicon, silicon tetrachloride. So what is CVD? Chemical vapor deposition. Chemicals, vapors are coming down onto the surface and then reacting and forming a solid. Okay. Now there's a reaction is right there. Can you see that? Silicon tetrachloride plus hydrogen. Now if you look at the chamber details, and you can see silicon tetrachloride. Can you see that? This box is a Cl4. And then hydrogen is passing through that. So the vapors of silicon tetrachloride, it's like a liquid, will pass through the chamber. Okay. And then you have, here you go. You have B2H6, pH3. Can you see that? These are boron and phosphorus sources for dopant sources. B2H6 is for boron, pH3, and arsenic, ASH3. Phosphine and arsine are for phosphorus and arsenic. So if you have to dope, then you have to add those gases. So they all go through this chamber, and inside the chamber there is a silicon wafer sitting on a graphite so-called susceptor. Now, what it does is, you see the RF coils? So when you send current through those RF coils, there's induction heating, and this graphite susceptor heats up, and then the wafers on top of will heat up as well. So what will happen is this gas will flow through this and then react onto the surface, and the solid will be formed. Now, having said that, now let us go to the theory. So what are the processes? First process is you have the growth species in the bulk. In this case is acetylene and arsine and hydrogen and all. And then the first point is diffusion from the bulk to the surface. Okay, so from the gas bulk, you diffuses to the surface. And then the second point is adsorption. No, it's not absorption, it's adsorption. It is surface binding of the materials. Now, after it is bound, it still is loosely bound, so it can still move. Now, you can imagine that if you have one atom of this or one molecule of this gas of whatever is come in the gas sitting at one point, you want it to be uniformly distributed over the surface, right? You want a uniform coating. So in order to that to happen, you need something called surface diffusion. Diffusion is simply a transport from a higher concentration to a lower concentration. Now, if you have diffusion, then if there are more material at one side, it will diffuse to the sparsely populated ones, and then you will get a uniform coating. So that is surface diffusion, which is very, very important. And it's still bound, but it's loosely bound. And then the fourth is the irreversible incorporation. It is the actual chemical reaction. Now that, of course, depends on temperature. And then after the reaction has happened, and then the byproducts, they have to dissolve. That is number 5. And then the dissolved byproducts will diffuse out. That is 6. Okay. So here we go. Now, if you look at it, now looking at that, then you realize what are the steps that are happening here. So, for example, silicon tetrachloride and hydrogen is coming in, and phosphine and arsine, they are diffusing onto the surface, and they're absorbing, then surface diffusion onto the surface, and then actual chemical reaction to form the silicon dioxide, and then HCl gas gets, it goes out. Now, what is interesting is if you keep increasing silicon tetrachloride, something funny will happen. There is another reaction that happens, it's like a parasitic reaction that is given by this. Silicon tetrachloride reacts with silicon to form SiCl2, which is a gas. So silicon tetrachloride can form silicon on the surface. Also, it can do what? It can etch. It can remove the silicon as well. So let's look at this story. Initial stages, if you have a little bit of tetrachloride, then silicon is formed. Can you see that? The growth rate goes up, and then it's a single crystal. If you keep going up, then the growth rate is too fast. It's no longer a single crystal; it's a polycrystalline film that is being formed. If you keep going up, now instead of growth rate going up, it's going down again. Why? Because some of them is getting etched out. If you keep going down, 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 at some point it will be mostly etching. So this diagram shows that yeah, even that is not simple as that. You have to control the flow rates and everything to make sure you get what you want to get. That is the moral of the story. That there's a whole lot of complexities. The diagram looks complex, but even there are more complexities in the actual chemical reaction. So that is about silicon. So you can get single crystal or polycrystalline. And then you have something called low pressure CVD. Now, so far we have talked about atmospheric pressure CVD. Now, low pressure CVD, of course, there is a problem. Now, low pressure CVD, if you look at it, the diagram looks different because you see there's a gas inlet, but also there is a pump. See the exhaust to pump. And what is the advantage of this process? Now, let me just talk to you theoretically about pressure. What is pressure? Pressure is simply the number of gas molecules hitting a surface, right? Now, what happens if you pump out the gases? Pressure will come down. Now, what happens to the gas molecules? They're still moving around, right? Because of thermal agitation. So, imagine yourself to be a gas molecule. How will it look like? You will travel in a straight line between collisions, and then will collide with another gas molecule, and then the path will change drastically. Now, what happens with the pressure is reduced. This difference, this length traveled without collision, that increases. So gas molecules can now travel to places where normally it would not go into, like gaps, because there is no collision with other air molecules. Okay, what is the advantage now? That means this process gas now can go inside gaps. You don't need to have like a steady flow of the gas because the gas now is traveling in straight line between collision and it can go inside the gaps. Now, so now what's happening? The wafers now are stacked. Can you see them? They're like stacked, like one after another, one after another. And now they'll be coated uniformly because the gas will now be able to go through the gaps. So LPCVD you can do the whole batch together. What is the disadvantage? Of course, now you cannot use the susceptor and the because they are all standing straight. It's not lying down on a graphite. In the other one, if you look at it, the wafers were lying down. Now it is standing, so you cannot use a susceptor. Then, of course, it's called a hot wall process. Now you have to heat up the walls. And so it is a resistance heater. Can you see that resistance heating? So what is the disadvantage of this process versus that one of the... So in this case, the walls are hot. So the chemical reaction will also take place on the walls themselves. So not only you will coat the surface of the wafer, but you will also coat the walls. Yes, that's why the chambers are rainbow colored. Yes, exactly that. So of course, what you need to do, you take it out, you etch it out, you clean it out, change the tubes, get back again. So that is the fun part. And then we are going through this plasma story. I will stop here today because I want another. So just give me another day, okay? Because yeah, whenever it is good for you, okay? Because this plasma, it will take some time. I don't want you to rush through. Go through whatever you have done today. Any questions? You catch me tomorrow. Okay? Thank you so much. Thank you. Okay? Okay.